Okay. Dear participants, we continue our morning session. So second talk is today is Yuan Miao from the Kavali Institute of Physical and Mathematics in Tokyo, more or less. This talk is titled Onsager algebra symmetries in six vertex model.
Okay, thank you very much. So, first of all, I'd like to thank the organizers for this very wonderful conference, and I'm very happy to be here. My first time in BIMSA, and really enjoyed a lot from the previous talks and discussions. I'm also very happy for the because my talk is after Robert's talk. Actually, many of the subjects actually the same, and since Robert has introduced a lot of preliminary knowledge, so I can actually save some energy. But anyway, so today I'm going to talk about Onsager algebra symmetries in six vertex model. Actually, there's another word behind that, which is at root of unity, which as you will see. And as Robert says, well, this is a very old problem, 30 years ago, but probably Onsager algebra is even older, right? So it's like more than 80 years ago, and I'll try to convince you that these two are actually closely related. There are some references. So I did this work during my PhD, working with Jules Lammers and Vincent Pasquier 4 years ago. But then at that time, I was more or less thinking about similar questions that Robert has been doing, which is the Q operator. But then, more recently, I came back to this question again, working with my collaborator Eric Venier in Paris, and we made some progress. So hopefully I'll show you. So first of all, as a disclaimer, I am a physicist, so maybe some of the things are not so rigorous as in mathematics, but hopefully the picture should be clear. So before proceeding to the technical part, so why we're interested in symmetries in quantum many-body systems. So I study lattice model mainly. So for that, maybe if you know the symmetries of quantum lattice models, we can study the phases of matter, which is some ground state properties. Or if we know the symmetry, we know some selection rules for correlation functions. And this is very useful if you do experiments. Actually, you can measure those things. And more importantly, we are interested in some dynamics of quantum many-body systems. We can study the transport or thermalization of these systems, and symmetry plays a very important role. It can tell us many things about it. So there are some examples. For example, there are some global symmetries in free fermion systems. So there's just U1 symmetry is number of fermions in one system. And it can be non-abelian. For example, SU2 symmetries in Heisenberg spin chains. But for mathematical physicists, maybe more nicely, there's quantum group symmetries in also in those quantum lattice models, such as Yang symmetries in Haldane-Shastry. But these quantum group symmetries are typically non-local, namely the density is probably bilocal, which is a bit difficult to study. So today I'll show you that for six vertex model at root of unity, which is also known as XXZ spin chains with a certain anisotropy values. These models have so-called Onsager symmetry, which is kind of in between of the SU2 and the Yang. So they are actually, sometimes they have local or quasi-local densities, but in the meantime, they are sort of infinite dimensional. So yeah, okay. So before doing that, I'll show you an even very simple model, which is a free fermions in the 1D lattice with periodic boundary conditions. So this part I hope everyone can enjoy at least a little bit. So the model that I study is the tight binding model. So the Hamiltonian is just C dagger C plus C dagger C. So just some fermions hopping in a 1D lattice. And I guess even if you never studied physics, it's very easy to solve this model. You just do a Fourier transform on this fermionic operator, and what you will get is that, okay, so all the eigen states are just creation operator of in the momentum space, which is denoted as Ck, and the dispersion for each mode is just more or less proportional to the cosine of the momentum of the particle, because we have periodic boundary condition. One thing you realize is that if you create a particle at momentum k and pi minus k, it has the opposite sign of the energy, so basically cancels. So it doesn't change the energy eigenvalues. So if you consider sort of this combination of the operator acting on any eigenstate, you will get another eigenstate with the same energy eigenvalues. And then I would like to choose a very specific kind of combination of the momentum. And the reason why I'm doing this is because the resulting operator is still local. So physically what it means is create a particle at side j and j plus 1, the neighboring side. But it might have a different phase depending on it. So basically how to get this is you just do an inverse Fourier transform of this operator. So it's very easy to convince yourself that Q or Q dagger commute with the Hamiltonian because it just doesn't change the energy eigenvalues. So basically this tells us is that there are lots of degeneracies. For example, if you start with any eigenstate, you can just add this Q or Q dagger or Q operator to it, and then you will get lots of degenerate eigenstates. So this is a very simple phenomenon in free fermion, but if you add interactions, so if you go, okay, I haven't introduced the model here, but just to illustrate that if you go to the interacting case, so this is some 6-vertex model XXZ spin chain. So for some system size with a delta which is some value, so you can see that here it's sort of related to root of unity. I'll show you in a moment. And this model is fully interacting. However, if you start with some high-speed states and you study kind of the so-called descendant states, which are degenerate with the same high-speed states, and then you will get lots of degeneracies. So you can count the numbers 2 to the power 4, if you wish. And moreover, within this subspace of the Hilbert space, you will see that all the excitations are kind of free fermionic. So you can there are some operators that create the excitation here, and then you can do it maybe multiple times. It will again be an eigenstate. So the technical term is that it's creating they create kind of exact Bethe strings known as Fabricius-McCoy strings. And this is some work that I've done 4 years ago, but today I will not talk too much about it, but all the phenomena are related. So come back to the free fermionic model. So there's the so-called Onsager. So okay, this is probably something should be in the textbook, but well, it's not. But today maybe you will know that for a free fermionic tight binding model, there's Onsager algebraic symmetry. So how could we see that? So we can define some operator called Q1 plus, which is exactly the operator I showed you before, that commute with the Hamiltonian. And then there's another operator that also commute with the Hamiltonian, which is Q1 0. So they are again some hopping Hamiltonian, but with the phase of I or minus I if you hop left or right. And if you consider a combination of this Q1 0 and Q1 plus and its Hermitian conjugate Q1 minus, together with the U1 symmetry, which is just the particle number, both Q1 naught and Q1 commute with the Hamiltonian, which is the hopping Hamiltonian. But what's really non-trivial is that if you check the nested commutation relations between Q1 and Q1 and Q naught, you will see that they satisfy this very nice relation. So so this adjoint QM means the nested commutator 3 times of QM with respect to Qn is proportional to just the commutator between QM and Qn. So this relation is known as Dolan-Grady relation. And in the early 90s, it's been proven by Davis is that so if you have 2 operators that satisfy the Dolan-Grady relation, it's equivalent, or there's isomorphism, to an infinite dimensional Lie algebra, which is with the generator AM and JN, where AM an commutator of am and an is proportional to some j with some shift, and the commutator between j and a will be 2 a's. So so this means that if you start with a naught and a 1, you can just generate a whole tower of infinitely many an. Yeah. So so as a side remark, so basically this algebra is a fixed point Lie subalgebra of a fine SL2 algebra, or actually SL2 loop group is also fine. So so yeah, so basically here, okay, I use Q, but you can what I really want to see here is that you can call this am and an. If you have two a naught and a1 satisfy this Dolan-Grady relation, it's equivalent to say there are infinite many an that satisfy all this algebra. And this algebra is known as the Onsager algebra because in 1944 Onsager used this algebra to solve 2D classical Ising model. And yeah, and then as you can see that, okay, also in the free fermionic case you can find a representation on a fermionic Hilbert space that satisfies the same algebra. So but here maybe I need to assume the periodic boundary condition plays a very important role. So yeah, so now what we can do is we can do a Jordan-Wegener transformation to the free fermionic Hamiltonian. So naively, if you do a Jordan-Wegener transformation, you might worry about the boundaries, but somehow in this story, boundaries are not so important. So basically, if you do the Jordan-Wegener transformation, you get this H tilde, which is just also known as XX model. But now, for the simplicity, I decided to do a unitary transformation to this H, which is again some XX model with a certain twist on when you hop. So there's a kind of a phase I. If you hop to the right or hop to the left, you get minus I. So in that case, the a naught and a1 I showed you in the previous slides becomes very simple. So they just become so a naught just becomes the magnetization. So this is very simple. And a1 is even better. So it just becomes this sigma x sigma x. And here, okay, I have to say that the Hilbert space is C2 to the power of L. So L copies of C2, and sigma xn means that there's a poly x operator acting on the nth C2. Okay, so this is exactly the one that, or equivalent to the one that Onsager studied for Ising model. So this is just the quantum Ising chain, which is the transverse field Ising model. And it's a very simple exercise that you can do is that a naught and a1 commute with the Hamiltonian H, and moreover, you can convince yourself that a naught and a1 satisfy the Dolan-Grady relation. So this implies that for this Hamiltonian H, there are infinitely many. Okay, first of all, it's an integrable model, and moreover, it's a free, kind of a free model. So there are always infinitely many abelian conserved quantities. That's implied by integrability. However, this Onsager algebra says something more. So they did not only have infinitely many non-abelian abelian charges, they also have some non-abelian charges that basically satisfy the relations of Onsager algebra. And another curiosity is that the eigenvalues of a naught and a1, these two operators, they are U1 charges, so they are quantized. So the eigenvalues of a naught and a1 are integers. So these are this is also a very interesting consequence, because if you look at the eigenvalues of H, for example, they are not integers, so they actually have some non-trivial dispersion. But for a naught and a1, they are just integers. So so now what I want to do is to so I showed you this very specific point of XX model. So I want to generalize it into arbitrary anisotropy parameter. So in order to do that, I need to define the so-called asymmetric 6 vertex model. So asymmetric means I have some field on the on both legs to make it kind of asymmetric, but it's more or less the same as the usual XXZ. So it's it's basically 6 vertex model defining on a vertex with 6 non-zero Boltzmann weight that you can choose. So it's 4x4 matrix, and I use the definition of omega to be q squared, which is very convenient for me. And T is the spectral parameter. Typically, in many other literatures, maybe the exponential of some parameter U. And usually, people use the UQSL2 generators to write this R matrix here. But there's kind of a strange thing is that somehow it's not clear how UQSL2 is related to Onsager algebra. Actually, there are some previous work done by a group in France by Bazhanov and others, where they study open spin chain. So I study periodic. So they study open spin chain where the model really has a quantum group symmetry, which is given by UQSL2. And there they find something called Q Onsager algebra in those models, but this is very different from what I'll talk about today. So today I'll really talk about Onsager actually. And and then the by using the R matrix, I can define a transfer matrix, a 6 vertex transfer matrix. That's basically the product of R and then trace the auxiliary space A. I hope this is standard in this community. And by taking the logarithm derivative of the T, I get the Hamiltonian, which is essentially the usual XXZ, but with a twist for that depending on the Q that you start with. So this Q is related to the anisotropy parameter delta in this very simple way. So it's just Q plus Q inverse over 2. And in this case, if your lattice size is mod 2L, then in that case you can always do a unitary transformation, as I showed you before in the XX case, to get just the XXZ model without a twist, namely all this part is just 1. So this is possible if your system size is proper. And for this talk, I always choose Q to be at root of unity. So it's exponential of I pi times a ratio of 2 coprimes. So it's very easy to see that Q to the power of L2 is either plus or minus 1 depending on the even or oddness of the L1 parameter. So namely omega to the power of L2 is always positive. So okay, I didn't write down the Yang-Baxter equation, but since everybody should know here, is that by using the Yang-Baxter equation of the R matrix, you can prove that the transfer matrix commute among different spectral parameters. And this means that if you do the expansion, then all the conserved quantities are also commuting. But these are all the kind of infinitely many abelian charges, as I mentioned before. Yes. So luckily, Robert already introduced the Tau2 model, so I'll introduce again, but in a very physics way. But anyway, so this model known as the KBBS model, so stands for Kopranov, Baxter, Bazhanov, Stroganov. More or less, there are 3 groups, K, B, and BS. They studied the model roughly at the same time, early 90s. And a very convenient way to write it is to consider a wild pair of this Z and X operator. So this omega, if you recall, is Q squared, and since Q is is exponential of I pi L1 over L2, so omega to the power of L2 is always 1. And in previous literature, people mainly focus on the principal root of unity, namely omega is exponential of I pi, 2 I pi over L2. But here I consider actually arbitrary root of unity. All these what I'll talk about works. So if we choose an L2 dimensional representation, this Z operator is just diagonal matrix. That's 1 omega all the way to omega to the power of L2 minus 1. And X is the clock operator, which is just a shift Z by some unit of omega. Yes. And it's easy to check that Z to the power of L2 and X to the power of L2 is just identity operator. So a big difference between this Lux and the one that Robert introduced is that in Robert's talk, this Tau2 model, there are only sort of 3 spectral parameters because they have to satisfy the chiral-Pulse curve. But here, I have 5 because I relaxed that condition. So if you relax that condition, it's still fine because I will show you that there's still kind of Young-Baxter to intertwine this Lux operator with the 6 vertex operator. So it's still a very useful thing. And for us, the relax this condition is very important because now there are 5 parameters, and all of the 5 parameters will factorize, similar to the previous talk, and they will be they will be related to the Onsager generators. So okay, so this looks a bit messy, but you will see that okay, there's I write this matrix in this. Okay, I call it a physical space, and A is the auxiliary space, which is L2 dimensional, and the physical space are spin 1/2 dimensional. Yeah, it is basically 2 dimensional. And I think in the previous talk, this Lux operator is rotated 90 degrees, so I rotated the other way to to do this, and exactly as explained in the previous talk, this Lux operator factorized. So factorized in a very nice way. So first of all, the dependence of y and y prime are just some exponential of sigma z, either on the left and on the right. So you can imagine that if you consider the transfer matrix, these 2 parts just factorize into some exponential of the U1 charge. And then there's the dependence on t plus and t minus. So there are some linear combination of u plus minus v. I use the exponential term just to compare to the 6 vertex case, but it really doesn't matter. So they're just some simple 2 by 2 matrices. And another very interesting part is I have this exponential of s in the middle of this of these 2 u and v matrix. Okay, and moreover, maybe compared to the previous talk, I interchanged the rule of x and z, but it really doesn't matter because they are just the same. Satisfy the same algebra. Okay, so then I can define the transfer matrix just by producing of this Lux operator and taking a partial trace over this L2 dimensional auxiliary space. So there are some simple nice properties of this this transfer matrix. First of all, there's a very simple Young-Baxter relation with the 6 vertex transfer matrix. So this TU is the 6 vertex one, and it commute with any Tau2 if you fix Q. So for fixed Q, they commute. So by Young-Baxter equation. But in general, the 2 Tau2 transfer matrices, they might not commute. And in general, if you consider, you can still write down a Young-Baxter-like equation, but unlike in this case, they really just intertwine. So there are 5 parameters for each of these lines, and they kind of exchange some of them and modify some of them, but not all of them, so they don't really commute. But this is fine because in the end, I'm interested in interpreting the transfer matrix of Tau2 model as some charges of the 6 vertex model. Right. So And then this is something that we prove. So I didn't show you the proof because we didn't do it as beautifully done by Robert before. But this is something that you can prove, which is we define something called T. Okay, sorry, I should always write T tau 2, but it doesn't matter. So so with the 5 spectral parameter, they always are tau 2 transform matrix. So if you consider this T, so T at all the spectral parameter 0 commute with everything. So this T commute with with all these transform matrices. And if you consider a 2 copies, so 1T times a generic T tau 2, it factorizes into very nice way. So okay, the first two is sort of trivial because as I showed you, the Lux operator has two. Sorry, it's very difficult to control. Yeah, okay. The first two part is the first and the last part is very trivial because the Lux operator just have factorized these two exponential of sigma z part, and this is what I call a naught. And you will see in a moment that why I call it a naught because it's really related to the to the Onsager algebra in the end. And then there's a part which is called T plus and T minus. So these are really just the Q and Q bar in Robert's talk. Yes, so this really similar role. So these T plus and T minus, they commute among themselves. However, they do not commute with A0 and A1. And A1 is kind of the additional part, right? So the A1 is sort of the, okay, first of all, it's not obvious why it's exponential of some operator, but we can prove it. And then it's exponential of some operator that's proportional to the that's basically has simple relation to the spectral parameter S, and times some operator A1. So this A1 here, I have to say that this is just some operator, and the property of this operator is not as simple as in the L. So for L2 equals 2 case, A1 is just sum over sigma x. But in general, for generic L2, this is not true. So A1 is actually a very complicated double sum of some operator, but it has been proven by previous groups that this A1 should be a quasi-local operator. Namely, it will be a double sum, but the support of the operator, the density of the operator decays exponentially. So this A1 still has kind of a pretty good locality. So they are not local, but they are quasi-local, and this still plays an important role in the thermodynamic limit. Okay, so I'll go back to Baxter. To Onsager algebra. So from the properties of this tau 2 transform matrix, we can prove that these two nested commutator between A0 and A1 are satisfied. So the Dolan-Grady relations are satisfied. And the way how we prove it is done by taking derivatives with respect to the S or Y parameter, and then using the properties of the tau 2 transform matrix, we can prove that these two relations are satisfied. So since this A0 and A1 are the A0 and A1 satisfy this Dolan-Grady relation, using the theorem of Davis, we can show that A0 and A1 is a representation of the Onsager algebra in this Hilbert space for any L2. Moreover, you can obtain infinite many generators by using the defining properties of Onsager algebra. So you might ask, is that okay? This Hilbert space is finite dimensional, so why do you have infinite many generators? So basically, what happened is that if your system size is L, maybe after a certain operator that's linear in L, your AN will be a linear combination of previous ANs. So in the end, but if you take L to infinity, then you really have infinite many generators. And I showed you that essentially tau 2 transform matrix commute with the 6 vertex transform matrix. Therefore, A0 and A1 commute with the 6 vertex transform matrix. So basically, if you wish, the 6 vertex transform matrix is in the center of this representation of Onsager algebra. Yeah, or it's a very simple consequence that the Hamiltonian obviously also commute with it. So basically, I just showed you that for a 6 vertex model at any root of unity, or equivalently XXZ model, XX spin chain at any root of unity value of anisotropy, has this Onsager algebraic symmetry. So, and then I'll show you something that physicists might care a lot, is about some applications of this tau2 transform matrix, is that there are some so-called non-invertible symmetries in the XXZ model at root of unity. So it's very easy to see already from this Dolan-Grady relation is that this A0 and A1 seems to there might be a duality that exchange A0 and A1. So if you change A0 and A1, it doesn't change any of the algebra. And basically what it means is it just change all the AN to A1 minus N. And this algebra will remain exactly the same. Yes. So basically what we want to find is some operator D acting on AN, and you get A1 minus N. Yeah, and also it's very easy to check that also this 6 vertex of Hamiltonian should commute with this D. And then this D is can be understood as some symmetry of this operator. But of course, the kind of the density. So the D is a sort of a non-local operator, but that's fine. So how to find this D? Well, we do not have a very systematic way of getting to that point, but we have some conjectures which we can check by doing the we can do this calculation explicitly on the level of the transform matrix, and then we can act on a different tau2 transform matrix. You can see it exchange the row of A0 and A1. So namely, it will exchange the row of S and Y. So that's actually what it does. Okay. So the answer is kind of simple. So you take the limit of your T plus. So T plus is the one that's basically the Q discussed in Robert's talk. But you have to rescale it and take U to minus or plus infinity limit. And I claim that this D is the operator that does this, or exchange the row of S and Y in the tau2 transform matrix. And what's really surprisingly is that if you consider DD dagger, so this is sort of kind of you want to consider kind of the fusion rule of this line operator. So there are some operators acting on matrix product operator acting on all system size, and what you get is actually a projector, which is just which is sort of it's related to basically the U1 charge that we have, which is E0. So the simplest example, which we don't need to use the tau2 relation to know that, is when we choose L2 equals 2. So in that case, delta equals 0 is the XX model that I showed you, and this D here is a very famous operator that we know. It's called Kramers-Warnier duality in the Ising model. What it does, it changes sigma x to sigma z to sigma x, and sigma x to sigma z. So this is actually a very simple operator, and it commutes with this twisted XX Hamiltonian. And moreover, in that case, DD dagger, is essentially just 1 plus the product of Z operator, which is a Z2 operator. And then it's basically a projector, so project to the even sector of this Z2 symmetry. And that's why people call it non-invertible, and it's related to the kind of a gauging of this Z2 symmetry in the condensed matter literature. And here we just have a kind of it's analog to kind of gauging a Zn. And as we know that this XXZ model at roots of unity is related to, in the IR limit is related to the C equals 1 free compactified boson CFT. And there, these models are really just orbifording of these CFTs. But I will not talk about that today. Okay, so that goes to my conclusion. So today I showed you that in 6 vertex model at any root of unity, there's a hidden Onsager algebra symmetry that, that has not been noticed until. Okay, it has been noticed in some specific case, but the proof for generic root of unity is really new in that sense. And there are some higher spin generalizations. For example, you can do the transfer matrix fusion relations to get a 19 vertex model, the homological Fatiev 19 vertex model. Similar story also present there. There's also Onsager symmetries in 19 vertex model. And of course, you can probably do it for even higher spin ones. And the proof that we give, it really highly relies on the KBBS tau2 model. So there's, of course, natural question is how this is related to the quantum group. And probably partially already answered by the previous talk by Roberts, that indeed this tau2 transfer matrix can be written as in terms of these cyclic representations of the quantum groups. A third remark is that is maybe more related to physicists, is that there's non-invertible symmetries at root of unity value of these models. This is also rather surprising because, people thought that, okay, these maybe non-invertible symmetries always appear in some more exotic models, but turns out that it's very universal, and it's already in this famous XXZ spin chain. And in terms of field theory, it's related to orbifording of the C equals 1 CFT. And actually, there's even higher spin generalization of this construction, which is related to a marginal deformation of the SE2 level K, where K is, K is the, 2s minus 1, yes. So for example, for the spins, 2s, so for spin 1/2, it is just K is level 1, and for spin 1 is level 2, etc. So, but then the orbifording picture there is not being kind of studied extensively, so this might offer some lattice realization of this field theory construction that we have. So, okay, that's all of my talk. Thank you very much for your attention.
Thank you for your talk. Do we have questions?
So is the Onsager algebra symmetry meant to completely resolve all the multiplicities you get?
Yeah, so basically it can resolve all the degeneracies that we found before, so of this figure.
Isn't the Q operator also meant to do that as well?
So Q operator does that, but the combinatorics probably not directly given by Q operator. And moreover, these Onsager generators could be the kind of the creation operator of these degenerate states. So, yeah.
And you understand enough about the representation theory of the Onsager to be able to
well, we're working on that.
Okay.
And, there are some previous work in the 90s.
Right.
Yeah. Yes. But yeah.
Okay. Thanks.
saying Onsager algebra. So
Yes.
this algebra is introduced in his paper in Ising model or what? Where is starting to use this Onsager algebra?
So it's not it's sort of introduced in the paper by Onsager in 1944.
Inside.
Yes, but then later in the 90s and 80s and 90s, people studied this again for the superintegrable Karl-Potts case.
Yes.
Yes.
The second question.
Yes.
Now, this you saying, for example, the Heisenberg model, spin 1 higher.
Yes.
One can prove that this symmetry.
So as you can see that for Heisenberg at isotropic point, it's sort of the limit when L2 goes to infinity.
Right.
Yeah. So in that case, somehow this construction fails. So you somehow need So this L2. Where is it? Yeah. So this Q, right? So if you take the isotropic limit, so this Q goes to 1. It's equivalent to say that this L2 integer goes to infinity. And then as Robert says in the previous talk, if you have infinite dimensional auxiliary space, it's very difficult to make sure that all the quantities are good. However, for any finite L2, this all works. So even for the 19 vertex model, so so for root of unity, this works, and you can actually write down the explicitly the generators of E naught and E1. And another kind of a remark that I want to make is that I showed you that there's this A naught and A1 that satisfy this Dolan-Grady relation. What's really surprising to me, or I have no idea how to prove, is that okay, A naught is clearly a U1 chart that has integer eigenvalues, but A1 is a horrible expression in the spin basis. However, the eigenvalues numerically, if you test them, they are still integers. So there's something happening, right? So, but we don't understand the reason at the moment. Yeah, there might be something like that. So, yeah, you're welcome.
Test. Okay.
Yeah.
So, can you go to the last slide where you introduced the Kramers-Wanier?
Yes.
Yeah. So, like this, the algebra that you obtained, this fusion algebra, looks a lot like the ZN Tambara-Yamagami.
Yes.
Yeah.
Yes.
It is. Would you say, or because you have A0, A1?
So, yeah. So indeed, so these operators just ZN and this D it seems to be the Tambara-Yamagami ZN version of Tambara-Yamagami. But we are not able. Yeah, it is related, but we are not able to say that this is that one. But maybe it has a bigger structure because I have many parameters.
Yeah, because I don't think
the
ZN Tambara-Yamagami that you have here includes the A1 operator, right? Because it's just
it doesn't. It doesn't.
Yeah. So I'm very interested in this A1. And also AN for any other N.
Sure. But I have to say that in the field theory limit, so this A1 in naught and A1 is sort of very robust on the ladders. But if you take the IR limit, somehow they start to commute. So this has been shown in the recent paper by Shuheng Shao.
Who starts to commute?
So in naught and A1 they don't commute, right? So but in the IR limit they start to commute. Yeah.
Okay.
So and then so in that case they become these two U1 symmetries in the C equals 1 CFT.
But for L2 equals 2, that's just the Ising model, right? Does that also happen in the Ising model, like what you just said? So
this CFT is not the Ising CFT. It is the CFT of this model of this model. Oh, sorry, it's very hard to control of this model. But in Ising CFT, it's really good. It's fine. Yes. So because Ising is sort of in the center of this this XX model.
Okay.
Yes.
Okay. Thank you.
Yeah, you're welcome. Sorry.
Yuan, it's rather very good remarks. I just want to make rather a remark. When I think there should be a possibility to see the emergence of this Onsager algebra, if it exists, by discretizing the disordered defects in 4D chain segments. After dimensional reduction, you will land on the effective chain picture where this, if it exists, and I think it's a very important question.
Okay, yeah, that's very interesting. Yeah, thank you. I see there's.
So I have some question about non-invertible symmetry.
Okay.
And so you only find this symmetry at root of unity.
Yes.
Right. And is it related to this KW duality, or?
It's a generalization of KW. So if you choose L2 equals 2, it's literally the KW. Yes. It's really the TYZ2 category. Yes.
So can I say if any lattice model that has KW duality will have this non-invertible symmetry?
Yes. If it's self-dual. You see that this is self-dual. So this operator is a duality for the Ising model,
right?
But it's a symmetry for this XX model. So it's sort of the self-dual point. If you have a model that is self-dual under this duality, then it is a symmetry.
Right.
Yeah.
So suppose I have this non-invertible symmetry. Does it constrain the spectrum in certain sense? Given rise to more degeneracies, or is it
not necessarily more degeneracies, but it does have some consequences. So.
Is it like useful symmetry?
Well,
yeah. Okay.
Well, it's very difficult. Yeah, can be useful. Can explain it to you later. Yes.
Okay. Thanks.
Okay. Thank you.
Other questions? Okay, let me ask something.
Okay.
About this formula, deep dagger.
Yeah.
When you say projector, you mean that if I square left-hand side, I have the same expression.
Sorry, can you say again?
You say projector, you mean if I square left-hand side,
yes.
I have the same with coefficient 1.
Okay, this case is proportional to projector. You get coefficients L2. Okay, fine. I mean, if you normalize this operator, it squares to 1.
Normalized and complicated, it's just some numbers.
Some number, some integer. Yes.
Some simple number.
Yeah, some explicit number.
Okay.
Yes.
Another question: can I express this D explicitly in terms of Mondrian matrices, not part like T plus, but whole Mondrian matrices? Can I express this operator D in terms of Mondrian matrices?
Mondrian matrices. Well, it's the transfer matrix, right? Just take the trace.
T plus, it's usual transfer matrix.
Yes. Is sorry, I forgot to mention here. So T plus is as you see there.
So it's transfer matrices.
Yes.
So you say that D can be constructed explicitly from RTT.
Yeah, at some value of the spectrum.
Yeah, but it means that from RTT, from case square root of unity, you have this extra operator.
Yes. Yeah,
and I probably have the last question.
Yeah.
There is a paper of Tarasov and for quantum fine algebras, and then generalized by the Bazhanov and Jimbo for elliptic case. They prove that in the case of square root of unity and elliptic analogues, they have extra centers. Extra centers of the algebra.
Extra centers. Oh, okay.
Yeah.
Okay.
Did you try to understand how your D operator somehow related to this construction, and probably if it's this in elliptic case?
Yeah, that sounds very likely is related to this. Yes.
Did you try elliptic case?
I don't have any let's say direct comparison to those results, but what you described to me sounds very likely is this. Yes.
Okay. Thank you.
Yeah. Thank you.
Okay, we finish. We have 5 minutes break.